Okay, students, now we'll see the channel capacity theorem. The number of bits transmitted through the channel is called as information rate, or we call as bit rate, right? You know that. The number of bits transmitted through the channel is called as information rate or bit rate. The maximum number of bits transmitted through the channel without any distortion. The maximum number of bits transmitted through the channel without any distortions, without any error, is called as channel capacity. This is the bit rate or information rate. This is the bit rate or information rate, the number of bits transmitted through the channel. The maximum number of bits transmitted through the channel is called as channel capacity. The maximum number of bits transmitted through the channel is called as channel capacity. So the maximum information rate is called as channel capacity. Now you tell me the channel capacity, the maximum number of bits transmitted through the channel without any distortion, without any error, is called as channel capacity, which means the channel capacity is greater than information rate, then definitely there is no errors. When the channel capacity is less than the information rate, then the errors will occur, right? Errors will occur. Therefore, the channel capacity depends upon bandwidth of the channel and signal to noise ratio. Now this is the channel capacity, where B is bandwidth of the channel, and where B is bandwidth of the channel, where S by N is signal to noise ratio at the output of the channel, signal to noise ratio at the output of the channel, or signal to noise ratio at the output of the channel is nothing but signal to noise ratio at the input of the receiver. Signal to noise ratio at the output of the channel, or signal to noise ratio at the input of the receiver. Now this is the channel capacity theorem, and this is also called as Shannon-Hartley theorem. This is a Shannon-Hartley theorem or Shannon-Hartley law, now which is given by Shannon and Hartley. Now this is called as channel capacity theorem or channel capacity formula, where channel capacity depends upon channel bandwidth. B is the bandwidth of the channel, where S by N is signal to noise ratio. Signal is affected by noise, therefore signal to noise ratio at the output of the channel, or signal to noise ratio at the input of the receiver. Okay. Now, if you want in terms of dB, then this signal to noise ratio is nothing but 10 log S by N. If you are doing, then you can get a signal to noise ratio in terms of dBs, but this is in terms of magnitude. If any dB is given, convert into magnitude. Okay. This is a Shannon capacity theorem or Shannon-Hartley theorem or channel capacity theorem. Okay. Not. So now we will see the channel capacity depends upon what parameter, and how the channel capacity is bandwidth and signal to noise ratio is depend. Okay. Now he is asking to find signal to noise ratio at the output of the channel is 15, and determine the channel capacity. The channel capacity C equal to B into log 1 plus S by N base 2, which is nothing but, now see here, now where bandwidth of the channel is 1 kHz, therefore this is 1 kilo into log 1 plus 15 base 2, therefore which is equal to 16 2 power 4 4 kilobits per second. Now this is C, which is equal to, now 1 mega, channel bandwidth is 1 megahertz, 1 mega into log 1 plus 15 base 2, therefore which is equal to 4 megabits per second. Now the channel capacity, which is equal to 1 gigahertz log 1 plus 15 base 2, therefore which is equal to 16 to power 4, now 4 gigabits per second. Then you understand here the capacity is 4000, capacity is 4 into 10 power 6, capacity is 4 into 10 power 9. Now what you observed here, now the channel capacity is directly proportional to bandwidth of the channel or not? The channel capacity is more when the channel bandwidth is more. That's why this is kilohertz. This is nothing but the channel is twisted pair cable. Now megahertz means the channel is coaxial cable. Nowadays everywhere we use optical fiber because of more channel capacity, because the bandwidth of the channel is more. Optical fiber cable, more bandwidth, more channel. Okay. In terms of kilo, mega and giga. Now there is a compromise between bandwidth and signal to noise ratio. Okay, so that you can easily understand while solving this particular problem. Now here is one question. An analog signal is band limited to, this is the signal which is band limited to 4 kilohertz, and this signal is transmitting through a channel using 8-bit PCM. PCM means what? Sampling, quantization and encoding. Sampling, quantization and encoding, and he is giving now 8-bit A to D converter, means n equal to 8. This is PCM system and transmitting through a channel using 8-bit PCM. And this is the channel. Signal to noise ratio at the output of the channel is given, at the output of the channel is 20 dB, which is given. Now this is in terms of dB, so if you calculate in terms of magnitude, signal to noise ratio, which is equal to 10 log, so 10 cancel. Now this is nothing but 10 power 2, which is equal to 100, because 10 log S by N, which is equal to 20 dB. Therefore, 2, 0, 0 cancel. S by 1 anti-logarithm 10 power 2, which is equal to 100. Okay. And the bandwidth of the channel is, and the channel bandwidth is already given. The channel bandwidth, which is equal to 10 kilohertz. Channel bandwidth, which is equal to 10 kilohertz. Okay. Channel bandwidth, which is equal to 10 kilohertz. So now what he is asking is, a sampling rate is 25% higher than the Nyquist rate. First we will find this one. Okay. Sampling rate is 25% higher than the Nyquist rate. First, what about the Nyquist rate? The minimum sampling rate is called as Nyquist rate, which is equal to 2 into 4 kilo, which is equal to 8 kilo samples per second, and the sampling rate is 25% higher than the Nyquist rate. 25% higher than the Nyquist rate, which is equal to 1.25 into Nyquist rate is 8 kilo. Now, which is nothing but 25% higher than the Nyquist rate. Now, this is nothing but 80 kilo bits per second. Okay. Now, this is the sampling rate. Now, this is nothing but 10 kilobits per second is the sampling rate. And what is the bit rate? For a P-SEN system, bit rate, which is equal to 1 by Ts into n, where which is equal to 10 kilo into n is nothing but 8, which is 80 kilo bits per second. Okay, 80 kilobits per second. Now, this is the bit rate. Now, here is the question. Now, check whether the error-free transmission is possible or not. What is the question is, check whether the error-free transmission is possible or not. If you want to check the error-free transmission is possible or not, now first we want to find the channel capacity. Now, what is the channel capacity? The channel capacity C, which is equal to B log 1 plus S by N base 2, which is equal to the channel capacity B is 10 kilohertz, which is nothing but log 1 plus S by N is 100 base 2. Therefore, the channel capacity here is 66.6 kilobits per second. What happened now? Now the channel capacity is 60 and the information rate which is passing through the channel is 80, which cannot withstand this channel because channel capacity is less than the information rate bit rate. Now errors will occur. Error-free transmission is not possible. Errors will occur. Error-free transmission is not possible. Now, so errors will occur. Error-free transmission is not possible. Error-free transmission is not possible. So what? So we want to, the information should be transmitting without error. So that's why he is asking the second question. Now determine. So if you want error-free transmission, definitely the channel capacity should be increased because the channel capacity is only 60. Your information which you are passing through the channel is 80. So now I want to increase the channel capacity. Now you tell me how to increase the channel capacity. You already have one experience. The channel capacity depends upon the bandwidth, and there is a compromise between bandwidth and signal to noise ratio also. So you should increase the signal to noise ratio or you should increase the bandwidth. Okay, that's why he is asking the second question. Determine the signal to noise ratio required. signal to noise ratio required value. Determine the signal to noise ratio required for error-free transmission. Required for error-free transmission. Error-free transmission is possible only when the channel capacity is greater than or equal to RB. Error-free transmission means C should be greater than or equal to RB. So now what should we do? Now if you want error-free transmission, channel capacity should be greater than or equal to this. Therefore, the channel capacity equal to RB. What is the channel capacity? The channel capacity is C, which is equal to B into log 1 plus S by N base 2. Therefore, channel capacity equal to RB. So C is nothing but RB means 80 kilo, which is equal to B is 10 kilohertz bandwidth. He is asking signal to noise ratio. So without disturbing bandwidth, 1 plus S by N base 2. So now here signal to noise ratio required is, signal to noise ratio required, if you do it 25 in terms of this is 24 dB. But actually what is the signal to noise ratio already given? 20 dB. What happened with 20 dB? If the signal to noise ratio is 20 dB, then you can get errors will occur, errors in the transmission, because signal to noise ratio is 20 dB. If I am choosing, then the channel capacity is less than the bit rate, errors will occur. So for error free transmission, then the signal to noise ratio required is 24 dB. Okay. So without errors, error free transmission is possible, whether you should increase the signal to noise ratio, and that's why he is asking another question. Now determine the bandwidth of the channel required. What he is asking is, now bandwidth of channel required, the bandwidth of the channel required for error free transmission, error free transmission. Bandwidth of the channel required for error free transmission. Error free transmission means definitely C is greater than or equal to RB, which is nothing but C equal to RB. Therefore, which is equal to C equal to B into log 1 plus S by N base 2. So C equal to RB, which is nothing but 80 kilo, which is equal to the bandwidth of the channel. We need to find log error free transmission. So error free transmission and the required channel bandwidth. Okay. So the bandwidth of the channel required for error free transmission means when you take the signal to noise ratio is constant, increase the bandwidth of the channel. We should see that this is nothing but S by N, which is equal to 100. So this one. So now the bandwidth of the channel required, the bandwidth of the channel required, which is nothing but 12 kilohertz. So what happening here? Then what is your observation? In order to increase the channel capacity, the channel capacity is increased. The channel capacity is increased. Now, if you want to increase the channel capacity, then there are two options for us. If you want to increase the channel capacity, we have only two options. So, increase the bandwidth. The channel capacity increased by increasing the bandwidth. Now, by keeping S by N constant, or the channel capacity increased by increasing S by N by keeping bandwidth constant. So by increasing bandwidth, automatically the channel capacity is increased. Okay. By keeping bandwidth constant, signal to noise ratio is increasing, effect of noise is less, therefore redundancy will be reduced and the capacity channel will be effectively utilized. Okay. Now this is the compromise between bandwidth and signal to noise ratio in order to increase the channel capacity. Note down. Now see here, this is the channel capacity. Now the channel capacity. Now one small question is asking. A communication system. Now the channel is affected by additive white Gaussian noise whose signal to noise ratio is far greater than 1. Then under this situation, bandwidth is B and capacity is C1. So now we'll see. Now what is the capacity C1 under this situation? The capacity C1, which is equal to B log base 2. When signal to noise ratio is far greater than 1, when signal to noise ratio is far greater than 1, we can neglect 1. Therefore, this is S by N, because this one is cancelled. Under this situation, now he is asking, under this situation, the signal to noise ratio is doubled. Signal to noise ratio is doubled by keeping B constant under this situation. Under this situation means signal to noise ratio is far greater than 1. Under the same situation, then what is the channel capacity? B is constant and he is asking what is the channel capacity? C2. Now you tell me what is the channel capacity C2. Under this situation, which is nothing but C2, which is equal to B is constant log signal to noise ratio is doubled, means 2 times of S by N. Therefore, which is equal to, can I write like this? B log AB log A plus log B. B log S by N base 2. So which is nothing but log 2 base 2 is 1. B plus, now what is B log S by N base 2 is nothing but C1. Therefore, the channel capacity C2, which is equal to C1 plus B under this condition. Now you know one thing, the channel capacity is directly proportional to bandwidth. So if this is directly proportional to bandwidth, what? If bandwidth is tends to infinity, channel capacity is also tends to infinite. No, it is directly proportional. Bandwidth is infinity, but channel capacity is not infinite. Not infinite. Now when bandwidth is infinite, then when bandwidth is infinite, now what is the C maximum, and upper value of C is upper value of C is dash, we want to find. So you know that the noise power, which is equal to K Tn into B, noise power, Boltzmann constant, thermal noise or noise temperature, B is bandwidth. Okay, can I write like this? This is the noise power by bandwidth. Now this is the noise power, which is equal to noise power by bandwidth, which is equal to K into Tn. Am I right or not? The noise power by bandwidth, which is nothing but K into Tn. Now this K into Tn is called as power spectral, power versus frequency. Power over a frequency range is called as power spectral density. Now this is the power spectral density. Units are watts power hertz frequency, watts per hertz. Now this is noise power spectral density. Noise power spectral density represented by eta. Now this is the power spectral density. Noise power spectral density. So this is represented by some eta. Now can I use this? Now what is the channel capacity? The channel capacity C, which is equal to B into log 1 plus S by N, which is equal to B into log 1 plus S by noise power. What is the noise power? The noise power, which is equal to K into Tn. Now can I write like this? This K into Tn, the noise power, which is K into Tn into B. Therefore, so can I write like this? This K into Tn, which is nothing but eta, is into B. So this is the noise power, which is equal to eta into B, and this is eta is nothing but noise power spectral density, watts per hertz. So can I write like this? C equal to S by eta. Now this is S by eta into eta by S. I just multiply numerator and denominator. Already B is available here, into log 1 plus S by eta B base 2. Therefore, X, which is equal to S by eta into B. So C, which is equal to S by eta into log 1 plus S by eta B equal 1 plus X base 2. Now this is 1 by X. Now C, which is equal to S by eta into, can I write like this? Log 1 plus X whole power 1 by X base 2. There is a formula of, now log 1 plus X whole power 1 by X base 2, which is equal to log E base 2. This is when X tends to infinite. Limit X tends to infinite, log 1 plus X whole power 1 by X is log E. So now here, what is X here? Now in our case, X is nothing but what? So you call it as X is nothing but S by eta B, right? Oh sorry, this is when X tends to 0. Now limit x tends to 0, log 1 plus x whole power 1 by x is raised to. Now see here. Now what is the relation here? Now which is nothing but x is inversely proportional to 1 by b. X is inversely proportional to 1 by b. When x is tends to 0. Now here when x is tends to 0, which means b is tends to infinite. Okay. So what is x here? When x is 0 is nothing but bandwidth is infinite. What is the meaning of that? When x is 0 here, b is infinite. Now which means that c, which is equal to s by eta. Now x tends to 0, which is nothing but b tends to infinite. When x tends to 0 means b tends to infinite. Log 1 plus x whole power 1 by x base 2, which is nothing but c, which is equal to s by eta log e base 2. So c, which is equal to log e, nothing but 1.44 something, 1.44 s by e, where s is signal power, signal strength, signal power, where eta is noise power spectral density. Okay, this is the noise power spectral density. This is the maximum capacity of the channel when bandwidth is infinite. But actually bandwidth is infinite, capacity should be infinite, but this is not infinite. The maximum capacity and upper value of the C is 1.44 S band. Sometimes he is asking, under infinite channel bandwidth, what is the channel capacity? In the question is mentioned under infinite channel bandwidth, then you should not do anything. Directly you can take this formula. Under infinite bandwidth, the channel capacity is 1.44 S by eta, where S is signal power, eta is a noise power spectral density. Okay, no. Now one question is like this: determine channel capacity, determine channel capacity of a telephony channel, determine channel capacity of a telephony channel, and the signal to noise ratio required is 30 dB, and signal to noise ratio required is 30 dB, and most of the time the students are doing mistake is 30 dB is directly substitute, is wrong. Now this is in terms of dB, but we want in terms of magnitude. 10 log S by N, which is nothing but 30 dB, then this 0 cancel, then log S by N base 10, which is equal to 3. So S by N, which is equal to 10 power 3, which is equal to 1000. This is okay. But what is the bandwidth? Bandwidth is not given in the question, but in the question he is saying that telephony channel. Now what is a telephony channel means? Now the telephony channel means a voice signal, am I not? Now a telephony channel means you have to identify that this is a voice signal. But what is the standard voice signal highest frequency which is used for all the standard systems? The voice signal highest frequency or voice signal bandwidth which is used as 4 kHz, am I not? Now for the standard systems, the voice signal bandwidth or voice signal highest frequency is considered as 4 kHz. Therefore, then the bandwidth of telephony channel means you should consider that bandwidth as 4 kilohertz. So here in the question, channel bandwidth is not given. Telephony channel means you should take 4 kilohertz bandwidth. Therefore, which is equal to 4 kilo into log. So this is base 2. Log 2 into 1 plus S by N is S by N, which is equal to 1000 bits per second. Now this is the channel capacity of a telephony channel, okay, of a telephony channel. Now that's why all the standard systems are already maintained. A highest frequency of voice signal is 4 kHz. Then what is the Nyquist rate? The Nyquist rate, which is equal to 2 omega, which is equal to 8 kilo samples per second. Therefore, if you use the PCM, so in a PCM system and digital techniques, then the bitrate is also fixed RB, which is equal to 1 by Ts into N. This is the sampling rate and this is the Nyquist rate. Now, to transmit our voice signal, now 8-bit PCM system is sufficient, 8-bit A to D converter is sufficient. Therefore, this is 8 kilo and use 8-bit PCM is able to transmit the total voice information. So therefore this is 8, which is equal to 64 kilo bits per second is the bit rate. This is the bit rate. This is the bit rate. That's why for each voice channel, bandwidth is allotted as they are taking a reference as 64 kilobits per second for a standard designing of a communication system. Okay. Okay. Now this is a channel capacity theorem or Shannon-Hartley law or Shannon-Hartley theorem. Okay. For a continuous we use this. Now for a discrete we are already finding entropy and utilization factor and all these things. Okay. So the this is the channel capacity or Shannon-Hartley law. Now the capacity of any digital channel is a compromise between a bandwidth and signal to noise ratio. Whether you should increase the channel bandwidth or whether you should increase the signal to noise ratio by keeping bandwidth constant or by keeping signal to noise ratio is constant. Clear or not? And if bandwidth is infinite, the channel capacity is not infinite because the infinite channel is not possible practically. So that maximum capacity of the channel is depends upon the noise power spectral density and the signal strength also, obviously. Okay, not on this.